I'm Grayson. I'm Mimi.
I'm Kara. And we're friends with...
And we're friends with Dustin George.
My name is Dustin George, and I will be telling you about the theory of helicopter flight. I'm sure most of you have watched a helicopter flying across the sky wondering how it aerodynamically stays aloft, or what happens if the engine fails. Imagine the year 1940, looking in the sky, wishing you could float up there with the birds, catching air, climbing and diving, back and forth for a few minutes. Well, I hope that's what Igor Sikorsky dreamed when he built the first useful single rotor helicopter. I will tell you about the challenges Igor faced while learning this theory of helicopter flight. I will also tell you about the drivetrain, the airfoils, pilot controls, and how we use them today. Air and lift. There are many challenges that come with defying the laws of gravity. So let's start with something we're all familiar with, air. Air plays a huge part in the lift capabilities of aircraft. Whether it's hot or cold, dry or wet, they all play a part in the lift of aircraft. Hot air, for instance, is less condensed than cold air. Wet air is less efficient than dry air, so helicopter pilots would rather fly in cold, dry air to get the best performance out of the aircraft. The next thing that comes into play with air is the air pressure, which is the weight of the air pressing down on the earth. At low altitudes, like sea level, gets you more efficiency than at higher altitudes. The reason being is that air molecules are squished together and they don't have to move as far to push off of each other. There's also more oxygen per cubic foot at sea level. Because there's more oxygen at lower altitudes, the engine is more efficient. The reason being is that with every intake stroke, the engine, it sucks in more condensed air. It's basically the same if you were to climb a mountain and suddenly be out of breath. The drivetrain of a helicopter. The next thing I'll talk about is the drivetrain. Every helicopter needs some sort of power system to create lift. When a helicopter overcomes weight, it's called lift. That's why it's crucial for aircraft to be lightweight. Every pound has to be overcome by horsepower to get it off the ground. To put that in perspective, the Robinson R44 Beta 2 puts out 245 horsepower and can weigh a maximum of 2,500 pounds according to Robinson helicopters. So for every 10 pounds of weight, it takes 1 horsepower to lift. This is, however, a D-rated engine for the reason it would simply have too much power and be a lot harder to control. The next factor in getting airborne is the airfoil. On a helicopter, this is the main rotor blades. Let's talk about how an airfoil works on an airplane first to make it a little easier. With an airplane, the wing is stationary. The forward airspeed causes the air on top of the wing to move faster, creating a low pressure according to Bernoulli's equation. This difference between the difference of air pressures on either side of the wing produces lift. Now when we talk about helicopters, we're moving the rotor blades, causing that same pressure found on the airplane wing on the main rotor blades of the helicopter. With the same differential pressure found on the airfoil, we achieve lift. So what happens if the engine fails? You just fall like a rock, right? Not exactly. The kinetic energy stored in the blades and the potential energy from the speed and altitude lets you auto-rotate all the way to the ground by disengaging the drive line through a part called the sprag clutch, in which the upward flow of air turns the blades. So as we create lift through the drivetrain of the helicopter, we also create torque in the opposite direction of rotation of the main rotor blades. If we didn't counteract this torque, the helicopter would essentially be a very expensive merry-go-round. There are a couple ways to counteract this torque. I'll talk about the most common, the traditional tail rotor. The tail rotor serves 2 functions. 1, it counteracts the main rotor torque, and 2, It is the main control we have about the vertical axes, which let you turn left or right. Now, how does a helicopter pilot control all these forces while airborne? First, we have our foot pedals, which control our anti-torque and yaw around that vertical axis. The next I'll talk about is the collective, which is controlled by the left hand. This usually has a twist throttle on it, just like a motorcycle. The collective controls the pitch of the blades by adding pitch by pulling up on the collective, or less pitch by lowering the collective. This is how we go up and down. Of course, when you pull a collective, you're adding torque, which will need to be counteracted by left pedal, and the same goes for lowering the collective and taking out power, which would require right pedal. If that's not enough, let's throw in the cyclic control, which controls the roll and pitch of the helicopter, or the movement around the lateral or horizontal axis. The cyclic is the next control I will talk about, and it is the most sensitive of all the controls, and only requires movement around the sides of a quarter in all directions. So now that I've talked about how helicopters achieve lift and how they're controlled, I will tell you about how they're used in the 21st century. Helicopters are used in many jobs, such as police, which can have thermal cameras, high-powered spotlights, and radios to communicate with cops on the ground. Firefighting is another job that is there to protect. With helicopter firefighting, there is usually a bucket slung from the underside of the helicopter. This can be filled by dipping it in ponds, rivers, or even swimming pools in people's backyards. There's a lever mounted inside the helicopter to drop the water precisely over the fire. Using helicopters for hunting is one that is used a lot in Alaska and Canada. Their main use is to drop off hunters in secluded spots where an airplane would be hard to land. Herding animals with helicopters has become more popular in the U.S. and Australia, especially with big ranches that have livestock spread over thousands of acres. Medevac helicopters have saved countless lives due to the fact they can get wherever they need in a lot less time than an ambulance. Using helicopters for conservation and relocation is also becoming more popular when there are no roads. There's usually a rifleman with tranquilizer darts hanging halfway out the helicopters to sedate the animal before relocation. So, whether you've noticed or not, when a helicopter flies overhead, they are here to stay and help in the day-to-day lives of people in every corner of the globe. Helicopters make our lives easier, safer, and more efficient. They make our towns, borders, waters, and countries safer. They can get you from point A to point B a lot faster than a car and land almost anywhere, including tops of skyscrapers. Igor Sikorsky's idea way back then was probably laughed at, but he managed to overcome and harness the theory of vertical lift. Today, I hope when you hear a helicopter overhead, you will think about the engineering that's gone into that aircraft and the lives that it could be saving at that point. This concludes my speech. Thank you.